we're going to be continuing our exploration of elementary probability theory and discuss a very important set of concepts known as stochastic processes and also a special type of stochastic process known as a martingale. So let's start off with the family for which a martingale is a part of, known as stochastic processes. So what exactly is a stochastic process? So if you already know what a random variable is, whether it be discrete or continuous, if you have a family or sequence of those random variables, then that family and sequence is called a stochastic process. More importantly, we have a couple classifications of stochastic processes. Two are extremely common. The first, in particular, for the stochastic process, notice that we have a sequence or family of random variables indexed with this parameter t, and let's assume that t belongs to this set capital T. So if t is a discrete set, you could also say a countable set too. Some people will define it as such. Then, if this t, or domain of the stochastic process, is a discrete set, then we call this a discrete stochastic process. And if the domain of this sequence is a continuous set, then we call this a continuous stochastic process. So, a stochastic process maps the set T to a set S. The set S, which is going to be the range of our stochastic processes, is going to be referred to commonly as the state space of our stochastic process. So let's look at a very basic example of stochastic processes that you actually probably already have worked with in the past. So let's suppose that our stochastic process xt are comprised of Bernoulli random variables, all of them. So Bernoulli random variables with the domain t, 1, 2, 3, 4, and so on. So in particular, t is the set of natural numbers. And let's assume that s, since we're working with Bernoulli random variables, obviously the range should be a binary set. Let's take the traditional 0, 1. Right? And let's assume that each of them have probabilities of success, and let's call them PT. Because x1, x2, x3, they're all Bernoulli random variables, but they don't necessarily have to have the same exact probability of success. They can all change, or they can all be the same. It doesn't really matter, right? So for example, if we're flipping coins, if they're all fair coins, then it's 50-50 for each. But you could just pick up random coins, and it's possible that some of those coins are not fair, so they might have different probabilities of success, right? So for example, let's assume that PT is equal to 0.501, and let's assume that's true for all t in t. And let's assume that this probability corresponds to, say, the probability of getting a heads, right? So if that is the case, then obviously the probability of getting a tails would be equal to 1 minus the probability of t, and that's going to be equal to 0.499, and that's again going to be equal to its complement for all t in the set t as well. So what exactly would our stochastic process xt look like? So it might look like h, t, h, h, T, H, T, H, T, H, H, and so on. Now again, this could be a finite set or it could be a countably infinite set. It doesn't really matter as long as it's discrete. And you could also code this in the binary fashion with respect to your state space S, right? So technically they would be equivalent ways of representing them. So H would obviously be equal to, let's assume that H is 1. So that's our success. And then 0, then 1, and then 1, and then 0, then, let's see, H again is 1. So 1, 0, 1, 0, 1, 1, and so on, right? So obviously that's a subspace of our state space T, and all of the values, T is equal to 1, because that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Those indices are a subset of our domain set T. Right? So this is an example of a Bernoulli, what we call a process. So let's actually just write this. So this is what we call a Bernoulli process, because it's just a stochastic process comprised solely of Bernoulli random variables, right? And also the domain of this Bernoulli process is a discrete set. So some people will also call this, as an example, of a discrete time stochastic process, right? So a Bernoulli process is an example of a discrete time stochastic process, even if you take these probabilities to be the same or different on each of these random variables xt, right? So stochastic variables or stochastic processes, very, very common, because one could look at this and be like, oh, this sort of looks like a Poisson sequence, or maybe if I take this to be a finite set, maybe even a binomial sequence. So a sequence of binomial or Bernoulli random variables, even if they're independent or dependent, would be an example of a stochastic process. So if you've worked with binomial or Poisson or even hypergeometric distributions, you've actually been working with special cases of stochastic processes, in particular Bernoulli stochastic processes. Now that we have a general idea of what a stochastic process is, now let us look at a very specific type of stochastic process known as martingale. So obviously this means that martingales are special types of stochastic processes. So all martingales are stochastic processes, but of course not all stochastic processes are martingales. So what exactly is a martingale? So a martingale is a special type of stochastic process that satisfies two properties. So if you have a stochastic process that does not satisfy one or both of these properties, then it is not a martingale. The first is that the expected value of the absolute value of each of the random variables must be finite for all random variables in that sequence xt. So that's pretty easy to think about, because there's some random variables or distributions that do not have finite expected values, or even finite second moments or finite third moments, and so on. And there's several examples, and I'll give you a quick one just in case you aren't familiar with such things, such as heavy-tailed distributions. But the second property is the real important one in this viewpoints of stochastic processes and moreover martingales. And it says that the expected value of the variable xt plus 1, so you can think of that as the value that the random variable takes tomorrow, given information about the variables today, yesterday, and every day before, is actually equal to the value of the random variable today. So the expected value of tomorrow is equal to the value of today, regardless of the things that happened in the past. Okay, so let's start off by looking at this first property to sort of give you an idea of a distribution that would not be a random variable and a stochastic process that would not be a martingale. So let's define, and examples like this are really easy to build. So let's define px of x to be equal to 6 divided by pi squared x squared, where x belongs to the interval 1, 2, 3, 4, and so on. Right? So is this really a probability mass function for some discrete random variable x, right? So obviously this thing is going to be greater than or equal to 0 for all x in the set of 1, 2, 3, 4, and so on, so the set of natural numbers. And it's also clear to see that pi squared, well, what exactly is pi squared? So pi is a little bit greater than 3, so pi squared is a little bit greater than 9. So that means 6 divided by pi squared is going to be less than 1, and obviously as x gets bigger, it's even more and more less than 1. So obviously px of x is obviously going to belong to the interval 0, 1, and that's obviously going to be true for all x in the set of natural numbers. So the first property is obviously met. But what about the sum of all probabilities? So let's take a brief look at that. So the sum from x is equal to 1 to infinity of pxx should be equal to 1, and if it is, then we have a probability mass function for some random variable x. So that's going to be equal to what? So that's going to be equal to the sum from x is equal to 1 to infinity of 6 over pi squared x squared, and obviously 6 over pi squared is a constant, so I can just factor that out. So we have 6 over pi squared times the sum from x is equal to 1 to infinity of 1 over x squared. And obviously what we see here, this is just the Riemann zeta function evaluated at, say, y is equal to 2. So we can just write that as 6 divided by pi squared times zeta of 2. And you probably already know the value of zeta 2. Zeta 2 is just going to be pi squared over 6. So we have pi squared over 6 times its reciprocal, and that's obviously equal to 1. So we have the first property there and the second property there. So obviously p of x is a probability mass function for this random variable. So you might be thinking, well, that's just fine and dandy. That means its expected value must also be defined as well. Because if you sketch out this distribution, practically what you're going to have is this, decreasing type of curve. So what would the expected value of this type of random variable be? So if that's the case, then that's going to be equal to, again, the sum from x is equal to 1 to infinity of x times the associated probability mass function evaluated at x. So that's going to be equal to what? So that's going to be 6 over pi squared, that coefficient in the front, times the sum from x is equal to 1 to infinity, and then we're going to have x divided by x squared, which is just going to be 1 divided by x. But what exactly is this series? So that's obviously going to be equal to 6 over pi squared times the limit as n goes to infinity of 1 plus 1 over 2 plus 1 over 3 plus all the way down to 1 over m. That's obviously a harmonic number, and we already know that the harmonic series diverges. So we already know that this goes to infinity, and you can use the integral test if you're not convinced of that, because we know that the integral from 1 to infinity of 1 over x dx is just going to be equal to the natural log of infinity minus the natural log of 1, which obviously is not a real number. So here we have a probability mass function for some discrete random variable on an unbounded domain whose expected value is not finite. Right? So if you have a stochastic process and one of the random variables in that process is this type of distribution, or for this type of random variable, then we have that that particular stochastic process is not a martingale because it does not satisfy the very first property. Now let's take a look at this second property for martingale stochastic processes, and that was that the expected value of xt plus 1 given information about everything, x1, x2, x0, all the way up to today, is equal to the value of today. So if we apply the expected value or expectation of both sides, what exactly are we going to get? So we're going to have the expectation of xt plus 1 given x0, x1, x2 down to xt, close brackets, and that's going to be equal to the expected value of xt. So what we have on the left-hand side, because we have the expected value of a variable with respect to stuff. So what exactly is that stuff? So if you recall the law of total expectation, it said that the expectation of x given y is actually just equal to the expectation of x. So that means the left-hand side is just equal to the expectation of xt plus 1, and that's going to be equal to the expectation on the right-hand side of xt. Right? So if that is the case, then what exactly do we have? So we have the expectation of t plus 1 is equal to xt. One can also show that the expectation of xt is equal to the expectation of xt minus 1. The expectation of xt minus 1 is equal to the expectation of xt minus 2. And we can mathematically induct this all the way down to the very first random variable, x0. Right? So what we have here is that if we have a stochastic process that is a martingale, that regardless of the value you are in terms of this, or position you are in this sequence, we have the same exact mean. So the means are constant. So we have constant means in a martingale. And that's actually very, very important. But moreover, the expectation of xt plus 1 will always be equal to the value we have today, right? So the expectation of tomorrow, given all of the information from today and the past, will always be equal to the value of today, right? And that's very, very important. Now let's look at another very useful property for non-negative martingales, and it's actually connected to a very important inequality known as the Markov inequality. So let's look at this theorem, and this is again called the Markov inequality. And it says the following, that the probability that x is larger than or equal to some number a, let's assume a is in the domain of the associated probability mass function, that's always going to be less than or equal to 1 over a times the expected value of the random variable under interest, assuming that x is a non-negative random variable. So let's actually see if we can provide a nice little proof for this, because this is actually very good approximation for probabilities. So firstly, we know that the expected value, let's prove it in the continuous case, and the discrete is going to practically follow similar. So the expected value for a PDF obviously is going to be integrated over the domain of x times its associated probability density function with respect to x. So obviously if we're assuming that x is greater than or equal to 0, we can re-represent this integral as the integral from 0 to infinity of x times f of x dx. Right? So let's also assume that a is some number in the open interval 0 to infinity. It doesn't really matter which number it is, but it's very important that we decompose this integral with respect to that number a. So we can write this integral as a decomposition from the integral from 0 to a plus the integral from a to infinity of x times f of x dx. So keep in mind that since we have a function, f of x, that's a probability density function, this is greater than or equal to 0 for all x in the domain of f. So since that's a non-negative function, each of those associated integrals, regardless of the domain, are also going to be non-negative too, right? So these are both greater than or equal to 0, regardless of the one that I have. So we have the expected value is equal to the sum of two non-negative integrals. So that means we can write the expected value of x to be greater than or equal to one of them, right? Because if they're both positive, if we take one off, then the expected value will be greater than the one that has its missing counterpart missing. So we can write this, if we focus on, for example, a to infinity, we can write that as the integral from a to infinity of x times fx of x dx. Also, keep in mind that x is going to be bigger than or equal to a because a belongs to the interval a to infinity. So that means that this is going to be bigger than or equal to the integral from a to infinity of a times the integral from f of x dx. A is just a constant, so we can factor that out. So that's going to be equal to a times the integral from a to infinity of f of x dx. And this is the precise definition of the probability that x is bigger than or equal to a, right? So it's equal to a times the probability that x is bigger than or equal to a, right? So we have the expected value of x is greater than or equal to a times the probability that x is less than or equal to a. So all we need to do is just rearrange this inequality and we get a result. So we have, by dividing both sides by a, because a is greater than 0, we have that the probability that x is greater than or equal to a is always going to be less than or equal to, important to focus on the directions that we have here, is going to be less than or equal to 1 over a times the expected value of x. And that completes the proof for the Markov inequality. Now, why do I bring this up in terms of martingales? So if, for example, xt is a non-negative martingale, then what do we have? Because keep in mind, the expected value of x can be represented with respect to x0. So if we replace x with xt, then we have that the probability that xt is bigger than or equal to a will be less than or equal to 1 over a times the expected value of xt. But by the sequence that we've already proven inductively, we have that if xt is a non-negative martingale by this Markov inequality, we have that the probability of xt greater than or equal to a will always be less than or equal to 1 over a times the expected value of the initial expectation. All right, so we have this very beautiful inequality for non-negative martingales. Right, so that's actually very interesting. Also, in terms of Markov inequality, you might recognize this type of setup with respect to a probability approximation known as Chebyshev's inequality. Right? So if you remember, Chebyshev's inequality gave us an approximation of probabilities with respect to standard deviations. And it said precisely that the probability that x is within k standard deviations from the mean, which we usually write x minus mu x is greater than or equal to or beyond k standard deviations from the mean. There's two usual variations of this, is less than or equal to 1 over k the quantity squared. So how actually to prove this very interesting result? And obviously this is only true or useful if k is strictly greater than or equal to 1. So we can actually prove this very easily with the Markov inequality. So what would that be? So we know that the probability that x minus mu x is greater than or equal to k sigma x, this is going to be equal to, if we square both sides of those relations, it's just going to be equal to the probability that the absolute value, or just the quantity, x minus mu x squared, will be greater than or equal to k squared sigma squared. Right? So we already know by Markov's inequality that's going to be strictly less than or equal to that number, because this is pretty much like the a in the Markov inequality. That's going to be less than or equal to 1 over k squared sigma squared times the expected value of the random variable that we're squaring, which is going to be equal to, or the variable including the square, of x minus mu, the quantity squared. But the expected value of x minus mu, the quantity squared, is just precisely the variance. So that's just going to be equal to 1 over k squared sigma squared times sigma squared. And notice that these sigma squareds cancel quite nicely. And we have that this is just equal to 1 over k squared. And that completes the proof of the Chebyshev inequality. So we have that the probability that you're beyond k standard deviations from the mean will always be less than or equal to 1 over the number of standard deviations you're actually considering. A very important and also basic example of a martingale is an unbiased one-dimensional random walk. So what exactly is a random walk? So you have a couple options here, and keep in mind we're going to be working in one dimension. So you can think about moving on the real axis. And let's assume that we start at 0. We can have -1, +2, +3, -1, -2, and -3. So you only have 2 options on each move. Either you move to the left or you move to the right 1 unit, with the initial condition that you start off at 0. So for example, you can start at 0, you can move to the right 1, then you can move to the right 1 if you really want to. But for example, after you move to the right 1, you could move to the left 1, 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 and so on. But on each iteration, you practically flip a coin, and then you look at, what's the probability that you move left, move right. It could be 50-50, or it could be 60-40, it could be 199, or so on. But nonetheless, that's what we refer to as a 1D random walk. So we're sort of stepping one step at a time in either the left or the right direction. And you can probably think about how the 2-dimensional random walk would work. So let's see if we can formalize a couple mechanisms associated to a 1-dimensional random walk to sort of understand why this is an example of a martingale. So what we're going to do is we're going to define PL to be equal to the probability of moving to the left. And we're going to define PR to be the probability of moving to the right. Right? So obviously those are the only 2 moves that you have, so that means they're complements of each other. So that means PL plus PR will be equal to 1. So if I give you 1, then you should be able to tell me what the other is. Okay? So let's assume that NL is the number of steps across your iterations t that are to the left. And let's assume NR is going to be defined similarly. So it's going to be the number of steps across t that are moved to the right-hand side. And from these 2, we're going to define N to be equal to NL plus NR. Obviously, if I tell you how many total steps I have made, and I tell you how many steps I moved to the left, then you should be able to tell me how many steps I moved to the right. In addition, we will define another metric that's also very important to model, and that's where we are on our axis, which we're going to define as the distance or position we are after n steps. So we're going to define dn to be equal to the distance, either positive or negative, from 0 after capital N steps, right? Now, with just the things that I have defined up to this point, I want you to pause this video maybe and see if you can define dn in terms of one or more of the variables that I have already mentioned, right? Because if you think about it, if it's positive, that means the number of right steps dominates the left. If dn is negative, that means the number of left steps dominates the right. So you should be able to show via these definitions that dn will actually be equal to nr minus nl. Right? So again, this is the distance after n steps. But also keep in mind that we can represent one of these in terms of the other and the number of steps n that we have. So if we replace nl, for example, we can write this as dn is equal to nr minus capital N minus nr. And we can obviously rearrange this by distributing our negative sign inwards, and we're going to have two nr's, so we can write dn with respect to nr. So we could write that as 2nr minus n. You could also write it in terms of d of nl as well. But it doesn't really matter, but technically most people go for the positive version of that. All right, so let's assume that we have our sequence, for example, left, right, left, left, right, left, and so on. And let's assume that this represents our stochastic sequence. So let's assume that we have n trials here. So what is the number of ways we can take n or nl steps to the left? So the number of ways we can take nl steps to the left, right? Because technically speaking, in this sequence of trials, either finite or countably infinite, the l's don't need to be in this position, but they can be rearranged as long as you keep the number nl fixed, right? So obviously if we have n trials and we're computing L, and this is obviously a binary event, then the number of trials is actually going to be equal to just a combination, because it really doesn't matter the order. So we're going to have capital N choose NL. And similarly speaking, capital N choose NR will be equal to the number of ways we can take NR steps to the right. Right? So that's very easy to see. Now, again, if I ask you, maybe we can model what is the probability that we take NL steps in a sequence of n? Well, that's obviously going to be a binomial distribution or a binomial random variable. Because if we look at that, then the probability of, let's assume nu L is the random variable, and then it takes value NL, that's obviously going to be equal to n choose little nl times the probability that we take L to the power of NL, so that's the number of successes in that sequence, and then we're going to have PR to the power of NR, but if we want to stay strict to the binomial structure, it's just going to be equal to capital N minus NL. Right? So this is the probability distribution for nu L, and you could similarly define, for example, nu R with respect to NR. It's practically the same exact thing, just a different combination and rearrangement of those particular, actually the same rearrangement of those, just, technically they're in swapped positions. Okay, so we have random variables nu L and nu R. So let's look at the expected value of those. So it would be the expected value of nu L, for example. So that's going to be equal to what? Now keep in mind, NL and NR could be the random variables if you have not simulated or walked through that random walk. Right, so I don't necessarily have to call it nu L, so NL could actually be the random variable, right? So it really depends on, have you observed it, have you not observed it, and so on. But regardless of which one you define it to be a random variable, this is still going to be equal to the number of steps that you take times the probability of taking a step to the left. And similarly speaking, the expected value of nu R would be equal to the number of steps that you take times the probability of taking a step to the right. And also, since we're working with random variables, you can also state the variance of these variables nu L. That's obviously going to be equal to n times the probability of success times the probability of failure. And that's actually going to be equal to the variance of nu R as well. They're actually the same exact thing. Right? So if I define the expected value of nu L and nu R, you could also technically define dn as a random variable too if you haven't observed it, and you can do delta n to be the random variable if you have observed it. So what would be the expected value of this random variable? So that's obviously going to be equal to, so what's dn? Well, dn is just the expected value of 2 nu R minus capital N. And if we distribute and use our properties of expected values, that's just going to be equal to 2 times capital N times PL minus N, because N is a constant. Obviously, you can rearrange this and you can write this as 2PL minus 1 times N, but it's practically the same exact thing. So, of course, whether these steps are independent of each other, usually we do assume that they are independent, because the only thing that really matters here is where you go next. For example, if we are located at position 5, and let's assume that this is where we are after, for example, 5 iterations of the sequence, and I say, what is the expected value of the value at x6? So where can we go on iteration x6? So obviously we're going to either move to the left at 4, or we're going to move to the right to 6. So you could look at that as almost a discrete uniform distribution. So what would the expected value of that be? Well, it would be the average of those two entities, which would of course be equal to 5, which is the position at 5. You should also see that the expected value, since we're working on that set, if you take the absolute value of left and right, you're always going to have a finite number because we're working in the set of reals. And obviously we see that this property, which is the second property for martingales, is clearly satisfied. So a one-dimensional random walk is an example of a martingale, but there's several other important generalizations of random walks and also several other examples of martingales that we'll discuss in the future. So I hope you enjoyed this introduction to stochastic processes and martingales, and I'll see you in the next video. Take care.